Welcome to the Consulting Specifying Engineer webcast, Critical Power, Standby versus Emergency Power Systems. This 60-minute webcast is sponsored by ASCO and Schneider Electric. I'm your moderator, Amara Razgis, Editor-in-Chief and Content Manager of Consulting Specifying Engineer and Pure Power. The topics that we will cover during today's webcast include NFPA 70, 99, and 110, NEC 700, 701, 702, and 705, and we'll also hear about generator sizing and loading requirement differences for emergency, legally required standby, optional standby, and COPS. Our speakers today are Gerald Versluys, who will focus on hospitals, and Dwayne Miller, who will focus on hotels, resorts, and casinos. I'm now happy to introduce our two distinguished speakers. Gerald Versluys is a senior electrical engineer and principal at TLC Engineering for Architecture. His areas of expertise include sustainable healthcare design and campus distribution systems. He is a member of the Consulting Specifying Engineer Editorial Advisory Board. Dwayne Miller is an electrical engineer with more than 20 years of engineering experience. He serves as CEO of JBA Consulting Engineers, and his areas of expertise include resorts and casinos. He is also CEO and co-founder of InView Labs, which focuses on advancing BIM technology. Thank you, Gerald and Dwayne, for joining us today. First, we'll hear from Gerald Versluys.
Thank you, Mara. Let me start with a little bit of a disclaimer. I have had over 20 years of experience, and I tend to generalize what I realize is a very complicated subject. So in the interest of keeping this brief and moving it along in the schedule that Amara has given us, I will make statements that there are exceptions to, there are other ways to work around. That's why we're all engineers. We solve problems. And so the idea is to share with you our philosophy on how we design generators for a hospital environment and what informs that design. So first off, generators typically are very codified for a hospital environment. All the accessories, where we put them, the environment that we install them in, and how we maintain them is written down. As Dwayne would say, it's prescriptive. It's like following a recipe. We see a lot of this language in NFPA 70, 517. We're also informed by NFPA 99 and 110. And as the slide says, it's all written down. It's easy to follow, and it's really not the scope of what we're going to cover today. What we are going to cover is how we take the information that we see in 517 on how to divide up our emergency essential systems into life safety and the critical, and then how we also address the equipment and the standby requirements for facility. Standby as defined by NFPA 99, level 2 non-life safety portion of the emergency system. So moving on, I'm going to base most of this presentation into what a traditional engineer is going to design. So traditionally, probably in the last 20, 30 years, we will use an open contact transfer switch. There is an option for less than 150 kVA that's permitted in the NEC to use a single transfer switch, but even in small hospitals, it's not considered a scalable solution. And plenty of jurisdictions, certainly I'm a resident in the state of Florida, do not permit that transfer switch is a breaker control type switch, or it is a traditional open contact switch. Transfer switches also require maintenance. This is, again, codified, written down, and one of the ways that traditional engineers have designed this is with a bypass isolation feature on the essential portions of the transfer switch. So most transfer switches to the date are open transition, and recently we've moved towards closed transition for our computer-intensive radiology department's diagnostic wings. So, getting some of the basics language out of the way, we're gonna move on to the real question that you probably dialed in is how a person starts out with a blank piece of paper and even gets to that sizing criteria. We have that first step is the essential branches, and how to determine N for the essential branches. The essential being life, safety, and critical as defined by 517. N needs to be online within 10 seconds. This limits some of the more complex solutions that Dwayne's going to talk to you about later, but really keeps it simple for the hospital engineers. We want those two branches to be online within 10 seconds, and most of our clients want it that way too. It's worth talking about that most hospital clients, facility directors, the people that are on the ground, want things simple. And even medium voltage, which those engineers like us tend to think of as straightforward and simple, makes them a little nervous. They always think about that engineer or facilities engineer that's on site in the middle of the night when there's a loss of power and something goes wrong. So can't stress enough that keep it simple, keep it real simple, and that's what has kept clients coming back to me, and that's what most of my clients share with me over and over again. So we talked about N. That is our essential, as defined by 17 loads, our life safety and our critical. And then we also have equipment loads, which have a less stringent requirement. They don't need to be on in 10 seconds, and are serving maybe important functions, air handlers that are maintaining pressures within the building, or other important but not life safety items. And so typical design from our firm will be to parallel a second generator in. This second generator doesn't need to be on in 10 seconds. It's not trying to save anybody's life, but it does have to come in, and there's other reasons to have that generator sized tightly to the load. Another evolving need within the hospital design community is chillers on emergency power. This seems obvious to a lot of us, but that a hospital facility has a lot of internally generated heat. Most hospitals don't have operable windows, and chillers are not required by code to be on the generator. So more and more we push to recommend to our clients that the chillers be connected to the generator, even if they aren't part of the primary function to be on that generator power. And we're going to see another reason to put all chillers on generators later. So this is one of those bold statements that will probably get me a couple texts and emails, but I can't stress enough that the size of a hospital generator is normally not driven by the load in the hospital. It is driven by the size of the largest transfer switch. And this may not be immediately obvious, but realize the most important thing in hospitals is that you coordinate your circuit breakers, selectively coordinate them, and the size of the largest branch that you serve is probably your chiller, if you're going to put that on the generator, or another equipment branch. Your overcurrent protection for your generator cannot be any smaller than that branch. So no matter what all the loads add up to, you've still got to have a larger overcurrent protection device on your generator, then you have the largest transfer switch that you've got sitting out there. So with all of that said, I'm going to talk a little bit about code-required testing, and we'll come back to the statement about calculating loads. Hospital generators are required to be tested, and they're required to be tested monthly, and they have some intervals in there, and they also have criteria for how to test them in NFPA 110. There is a requirement for an annual test, but that's only if your minimum load on the generator is less than 25%. Some facilities follow that guideline just as an added protection and confidence builder, but certainly not required if you've designed your system and sized it accordingly. That goes back to sizing your generator down to your loads. So why does this testing matter, especially when we're talking about sizing generators, is because the generator spends the majority of its life, its run hours, serving the testing function. Unless you're in Florida like me, and then the generators get a little bit of a workout. But the generator typically is tested monthly, and that is the majority of the function for that generator. The other reason testing matters is because the load that you test with must be sufficient to keep you above that 25%. That 25% requirement, and that is avoids wet stacking and gets your exhaust temperature up high enough. And testing also gets a lot of bad dissatisfied comments from the hospital users because it bumps everything. So what it really brings to light is the difference between the design demand and the real world demand on the generator. A lot of the calculations that we do when we submit our plans to our code officials are guided by NEC as well as our experience. Some states, jurisdictions actually give you a worksheet on how to add up your generator loads, but you, in general, are going to show on paper a larger load on that generator than when they test it is going to show up as a real load on it. Why does that matter? Because what's going to happen is you're only going to be able to load that generator in its monthly test to a portion of what you've designed it to. So any given day, not so much life safety, but the critical loads will only demand about half of what you've calculated as your demand load. And we know this through experience, and this is also exacerbated by the empty loads. You're not going to start the fire pump every time you test the generator. A lot of times ORs, cath labs, and that, you're not going to test those transfer switches during the testing. So what we end up with is, certainly as far as the facility engineer's perspective, is that the generator looks oversized. The generator is only seeing 25-30% of its capacity tested each month, and that's hard on a large diesel engine because when they're in those low ranges, they pass a lot of oil into the exhaust. That's the term wet stacking. And if that temperature doesn't get up high enough in the exhaust manifold, it actually shortens the life of the generator itself. So by testing it, you're shortening the generator's life. So how does this impact the engineers that I have on the call, and how do they work around it? Hey, I've figured out I've added up my life safety and my critical loads. How am I going to now make sure that when they test that generator every month, that I'm not only loading it up to 20%, that I'm getting more load to it? Well, one of the things is, as suggested, parallel two smaller generators, as long as you're still keeping the size large enough to permit that coordination to happen on your selective overcurrent protection. And then the other thing is give access to the emergency board from your normal loads. This has become real commonplace to actually give a manual process to your facilities engineer. Kirk Key interlock might be a term that some of y'all are familiar with, to artificially load that generator whenever they test it, monthly or annually. So that solves two problems at once. One, once you make that manual connection between the emergency board and the normal board, you are giving the client access to full backup power. Obviously, you can open the main, serve the whole facility, commonly called island mode, and in the space of definitely gives you in the wake of several disasters a real reason to give that facility that mode. It's a break from the traditional dogma. I'm getting requested more and more often. We not only want extra emergency power, we want to power the whole facility off of a generator. Now, a lot of the reasons that we've been doing this as opposed to recommending a load bank or another method of testing the generators is because it gives that client confidence that he can power up his whole facility. There is a little bit of a hook on that. Two problems, challenges. One is when you've added the manual connection to backfeed a main service or a normal branch from the emergency switchboard, you also still have to maintain that overcurrent protection coordination. So that means that whatever sizing criteria you used for your generator breakers in your emergency side, you need to now follow that on the normal side, where now a lot of the testing is able to, or that now that the coordination study is able to function correctly, you can't have a breaker larger on the normal side than you would have. So with that, I'm gonna go ahead and pass the presentation over to my partner, Dwayne.
All right, Gerald, thanks so much. That was a terrific presentation, and we will now move this on to Dwayne Miller. Dwayne, you want to take it away?
Sure. I wanted to, I think Gerald did a really good job at running through for hospitals, and we're going to look at now is a little bit more of traditional systems that we would be doing for a non-hospital environment. One of the things that we do a lot of work with is large-scale hotel resorts, and a lot of times we'll end up, Gerald referenced that, people want full generator backup. Some of the remote locations we work in, we end up dealing with a lot of that, which is really fun, interesting, creative stuff to design. So some of the things that you hear me talk about, if you've got questions on it, it's based on, our practice here, also in Asia and other parts of the world where we do quite a bit of large-scale systems. When we talk about a large-scale system, and it's not a hospital environment, as Gerald covered, you take a look at NEC 700 for emergency, 701 for legally required, 702 for optional standby. Those are the primary codes that are going to drive us. 700, very prescriptive. It's very limiting with respect to what you're allowed to put on the true emergency system. Legally required is also very prescriptive, driven, if you think about what the purpose of those are, which we'll talk about in a little bit, it's clear why they would be as prescriptive as they are. When you get into optional standby systems, that's where you're really starting to look at, you're looking at what's the business need? What are we trying to protect for that owner, and what does he want to be able to maintain operations on in the event of a utility outage or failure? So if we talk about 700, again, the purpose of it is loads essential for safety to human life. That's pretty clear. It's an automatic system, so it's got to be online in 10 seconds. Again, limited to code-specific and mandated loads. From a segregation standpoint, when you're designing for emergency power, it's got to be segregated from all non-emergency. It's a little different in hospitals. Gerald was talking about where you can take life safety and critical branch and put it on one system where equipment is separate. For 700 and 701 loads, they're actually required to be segregated from each other. Protection of feeders and equipment, the code's very specific about how you have to protect feeders and the equipment that makes up the emergency system. And then one of the things that for bigger system becomes a bit of an issue is that it's typically a very small fraction of your load. Most of the designs that we do, we're taking either 12-470, 11 kV if it's international, or 22 kV, and we're distributing around the property both emergency, your legally required, and your optional standby, or business critical, as they call it in Asia. So when you've got such a small fraction of a load on a system that is really designed for more bulk distribution, it becomes interesting as to how you have to address that. One of the things that they did in the Las Vegas market a long time ago is they actually allow us at the 15 kV level to combine emergency and legally required into one system because it's more practical. When we talk about 701, the purpose of 701, we need to avoid hazards or hampering of rescue or fire operations in the event of a power outage. These are also automatic systems, but now we have 60 seconds, which is really good because it lets us stagger some of the big loads that make up this system from your lighting and your alarm systems and those systems that are really all about preserving life. It's driven by municipal, state government, and then also the AHJ. The AHJ in a specific jurisdiction. I'm sure Florida is a bit different from Vegas. You go to California and you deal with either OSHPD on the hospital side or some of the local agencies. It's very different depending on the geography that you're in, and then different again when you go international. Legally required, it's got to be segregated from your emergency, and again, this is typically a fraction of the system load. The prescriptive nature of both 700 and 701 just inherently limit, how much load you're actually going to have on those systems. When we talk about 702, now this is where systems get really interesting, and it goes all over the board. Every owner has a different expectation with respect to how their property is going to behave. We've done, over the past 30 years, multiple large-scale resort developments, from Atlantic City to Vegas to, some stuff we've done in Connecticut and in Macau and Hong Kong. Every owner is different with respect to what they want. So it's intended to supply loads where life safety does not depend on performance of the system, and that's an important distinction to make. So you wouldn't have any fire services loads really that are optional. It can be automatic and or manual. There's really no time requirement. And again, primarily driven by business needs. And internationally in Dubai, Hong Kong, external to the U.S., they typically refer to this system as business critical. It's got to be segregated from emergency. It can be intermingled with your 701 loads, but it cannot be intermingled with 700. This is going to be the bulk of a large system load. It's going to be those things that the owner wants to make sure they can maintain operations in the event of a power outage. So what type of systems do you, obviously discussing all the different alternatives and options is beyond the scope of the time frame we have today. But really there's two ways to look at it. There's distributed systems, particularly when you're talking about a property that may be anywhere from 5 to 10 million square feet all in. You can do that with multiple generators and independent subsystems, and it's typically the generator then is tied to a specific portion of the facility. It's also going to be set up with transfer switches for the emergency, legally required, and critical or optional standby that basically define those subsystems within the zone of the building it serves. Some of the advantages or disadvantages of this type of system, if you have one generator failure, you lose a portion of the facility. One of the advantages is it's simpler. It's easier for the operators to kind of get their minds around single generator, group of transfer switches. Most operators, are very comfortable with that. When we move into parallel, or what I like to call an aggregate bus system, it's typically comprised of multiple generators. You've got a common generator bus. We would typically segment that bus so you can isolate it from your load bus and also isolate it from itself, depending on how big the system is. And now you're really looking at a system that is global in nature. It serves the entire facility, the entire property. So when we look at distributed systems, Again, it's dedicated to a portion of the facility. It's a single generator subsystems. You've got transfer switches involved. It's actually increased maintenance because now you've got multiple locations you've got to go to test and to maintain the equipment and the transfer switches. From a loading standpoint, one of the things that makes it a little different is you actually get lower utilization on your engine typically, because now you're doing a calculation for a portion of the building. You're not getting the benefit of a kind of an aggregate diversity that you would take over the entire property. So you end up with your generators being a little bit lighter loaded. Testing challenges are the other issue. Again, multiple locations that you've got to go test, multiple portions of the facility that you have to disrupt. Unless you go with closed transition transfer switches, which, we've seen both. There's certain large-scale properties that their approach is you go with code minimum. We don't care if our casino is down or if our hotel rooms are down or if we can't get to the central plant. If we have an outage, we're worried about first cost. And typically, a distributed system for a large-scale property will be driven by first cost. The other is, again, it's a simpler system. It's easier for a property operator to get their head around a generator with a series of transfer switches. Okay, and that occurs 5 times across the property, sometimes a little bit more within their comfort zone. And we're talking about a parallel or aggregate bus system. One of the major benefits of it is really robust load response. Gerald talked about the 10-second requirement, which is also, in Article 700. One of the ways that we would typically set the system up is that your load bus would be serving power to the source under normal operating circumstances. So you would have a utility feed that ties to your load bus, then you would have a gen main, and that becomes your transfer pair between the generator source power and the utility source power. But you can, for your large-scale loads that we would have in the 702, you can delay those until you have an engine count online that you're comfortable is going to be able to deal with the starting characteristics of that bulk load as you close those devices in. So load prioritization becomes, you can do some really interesting things. And for the 10-second loads, typically the way you can set it up, there's multiple ways to do it, but one of the ways I like to do it, the load bus is active when you're on normal power. You lose normal power. Every device but your emergency device opens, and as soon as that first generator attaches to the bus, it takes over the load. And typically it's sized, we're talking engines, anywhere from the 1250, 1500 to 2 meg range that we would typically use to create a large-scale load bus. You can also maximize utilization of your engines because you've got real-time demand management, load management that you can have within a paralleling arrangement that typically you wouldn't get with a distributed system. I do want to mention, you can also do cold bus paralleling, and that's where your generator bus on your smaller systems that we do for paralleling, your generator bus sits dead. When you lose your load, you may have transfer switches downstream. You create the aggregate bus with the generators, and then you distribute through the transfer switch in a more conventional approach. It's kind of a hybrid of the extreme paralleling system and the traditional system of generator with transfer switches. There's a lot of system flexibility you can build into this. Typically, we would use power circuit breakers as transfer pairs. Those are power devices, and actually the type of breakers that you're going to rack out, they're actually designed and intended for switching purposes. Some of the disadvantages, it can be very complex, and Gerald referenced the KISS principle, and there's ways to execute the KISS principle within this type of system, which we'll talk about a little bit later. The other is, it is expensive for a property operator who, if their casino is down, is going to lose, multi-millions of dollars an hour. They're usually willing to make the investment. Has been our experience. When you start to look at the design considerations, we talked about code requirements, NEC 700, 701, 702. 705 becomes important when you look at doing closed transition paralleling. We do a lot of closed transition, both domestically and internationally. The benefit of the closed transition is you can go between the generators and the utility without disrupting the load. That becomes a huge benefit to the property, particularly when an open transition bump creates all kinds of operational headaches. So we've closed transition you can go with, and you have to look at 705 and also talk to the local utility provider. Southern California Edison has their specific rules. If we're going to go closed transition with them, Nevada Power is different. CEM in Macau is going to have a different set of criteria they want you to follow. The business needs, and this is where we really have to behave like consultants, and we have to go in and really get the owner to express to us what their expectations are in the event of a power outage, and then also work with them to ensure that their needs that they're expressing is aligned with the budget that they're anticipating, which typically that's where the major disjoint occurs. System voltage is a consideration. If you're going to do bulk distribution for a large property, typically you're going to end up with 4160, 13.2, 12.47, some sort of 15 kV nominal, or 22, something in the less than 25 kV is what we've typically worked with. If you look at maintainability, selectivity, and flexibility in this system, one of the things you really have to focus on is how do we minimize and eliminate common mode failure points. When you go with an aggregate system, you don't want a fault on one bus to make the entire system collapse, because then the whole property is sitting in the dark. Load prioritization, legally required, emergency 700 is going to be Pri 1, your legally required Pri 2, and then all the priorities after that are really driven by what the owner expectation is for the property. One other issue is that when you design the systems and you specify them, they need to be inherently safe. If an operator goes up to a board and tries to close in two sources that are out of sync, depending on how far out of sync they are, that could be a line-to-line fault, which in electrical terms is bad. So you really have to make sure that they're not able to do something that's unsafe, and that's usually done with interlocks, with sync check. I mean, there's all different ways that you can make sure that the gear is inherently safe. And ASCO, Russ Electric, your more prolific vendors out there are pretty familiar with the hardwire technology that needs to go behind the programming to keep the operator safe. So generator sizing and system capacity, again, 700 is very prescriptive. You've got to be able to pick up the entire emergency load simultaneously. 701 talks about adequate capacity for loads intended to be operated at one time, so it's kind of like a coincident peak evaluation. Then you get into 702, and they're really telling you, well, you need to run the typical calculations that you would run. On the medium voltage systems, a lot of times what we will end up doing is leveraging historical data and showing that to the authority having jurisdiction, so they understand that, the connected load is X, but as Gerald referenced earlier, if you look at connected and you look at demand, you're anywhere from 30 to 40 to 50% of that calculated load is your actual running load. And if you size a 15 kV system for calculated load, nobody's going to be able to afford to build them, which is why the utility doesn't follow that approach and actually falls under a different code in terms of how they size. It's not based on NEC. Automatic load management is another thing that you can do with the aggregate system that is really beneficial. If you should lose an engine, you can actually, real-time demand management, drop loads off that are the lowest priority to keep the system working. And when you're doing your sizing, and this is probably more for Gerald, it's much for me too, because there's so much harmonic content that makes up a lot of the loads that go into these larger facilities. You really need to take a look at your harmonic load profile and what are your harmonic generating devices and equipment. What kind of filtration is in place on, say, variable speed drives? How are we mitigating the harmonic impacts of UPS power, which typically you're going to have on the generator? NEC 705 really has a good dialogue on some of the things that you need to consider and some of the things that you probably need to be speaking specific to the manufacturer that's going to be leveraged on the job. With input filtering and some of the different techniques that are out there, as long as it's addressed appropriately, this can be managed, but I incorporate it more for awareness than anything else. So deployment is huge, particularly as systems become more complex. Factory acceptance testing when you're doing a parallel generation system it's a must because what you really want to be doing is testing that equipment in a controlled environment at the plant and simulate all of the different control functionalities that are made up in your sequence of operation. And actually, our firm, what we do is when we go to the factory acceptance testing, we try to break the gear. We try to make it do something that it shouldn't do, really kick the tires hard. And the nice thing about doing that in the factory is you don't have building load connected, you don't have all the chaos that's going on towards the end of the job, and it's in a controlled environment where they can make changes. And the goal of this is that you test and really kick the tires hard on that equipment before it shows up on site for field commissioning. And ideally for field commissioning, what you should be worried about is connecting the equipment all together and then running it as one global system. And then the other thing is you've got to be ready for acceptance testing with the authority having jurisdiction. And depend on who that authority is, they're going to have different criteria. In Las Vegas, they'll hit a shunt button, drop the entire building into the black, and time to make sure that the emergency loads come on in 10 seconds or less. And then the handover is really important. When it comes to the KISS principle around paralleling switchgear, there's a couple of things to really focus on. Our philosophy and my personal philosophy has always been to keep the complexity as isolated as you can. So within the paralleling switchgear, that's where we do all the automated control for the 15 kV devices. Unless I'm pressed really hard, I won't take that distributed control beyond the paralleling switchgear and the generators unless the owner really wants to drive it. It's always, I have this picture in my head of distributed control of 15 kV devices and Homer Simpson in the control room with a donut pushing buttons while people are out there actually working on the equipment. So my personal take on it is to keep it safe. If we can limit the complexity to just the paralleling switchgear, that's a very controlled device, very well designed, very robust, and easy in terms of the interface that the operator has to do with it. I think that's a prudent approach. So when you're looking at that handover, really helping the handover, and this is a joint effort between the engineer and the provider of the equipment. ASCO will send out field techs, or Russ Electric who will help make sure that there's training, and you need to include a training component in your specification. Also, at this time, you would want to make sure that you had an ongoing maintenance because this gear is complex. Typically, you're going to have people on site who may be able to maintain it and run it through its monthly testing. But if there's a PLC problem or some sort of real technical problem inside the equipment, you need to have readily access to the vendor and the equipment provider. And then operational testing. NFPA 110 goes into a lot of what you've got to do for testing, and we'll talk about that a little bit more in the next slide because operational and functional testing is critical to making sure the system's going to be available when it's called upon to run. So when we talk about testing, Gerald referenced NFPA 110 and testing under load. One of the other reasons that we are on large-scale systems, we're very big proponents of closed transition paralleling, meaning that it's make before break. Obviously, if you have an outage, the system is out, but when it comes back on generator, when the utility is restored, you can go closed transition. That eliminates one disruption. For testing purposes, if you're in closed transition mode, you can actually test the system under load, run all the transfers through the transfers that they need to go through without disrupting the facility. In our experience, the larger systems that are open transition, what ends up happening is inevitably they don't test. Or if they test, they go in and they just start the generators, which is actually probably just as bad as not testing. Testing it under load, taking it under full transfer of its equipment, and then having a live load bus. A live load bus now serves as your load bank, so you can definitely get your engines up to the capacity that's required to ensure that you're meeting the minimum load requirements in NFPA 110 dictates for minimal capacity for testing under load. One of the benefits with hospitals, you have an organization like the Joint Commissions who are actually really keep a close eye on what happens with hospital generator testing. It's not really that way with your large-scale resort properties or other types of buildings. The local authority having jurisdiction is really probably your biggest driver on it. So setting a system up that can be tested with minimal impact to the business or the property is a huge benefit that I think you can incorporate much better with a large-scale aggregate paralleling system than you might be able to with a single transfer or multiple transfer switches, single generator, distributed versus aggregate. And then, building load as a load bank, it really offsets cost. Having the capability of hooking in an additional load is a big benefit. Being able to leverage the optional standby loads for a facility to make sure that you can really drive the generators up to 80% if you want to do that on an annual basis, just to really clear them out. It's a pretty large topic to cover, and I'm sorry if I've spoke too fast, but it's exciting stuff. And the thing I like about the large-scale paralleling systems is they're just fun. When you're designing, 20 megawatts or 30 megawatts and distributing it across a property, you can do some really neat things that you don't always get an opportunity to do for a smaller-scale system. So that's about all I have. Look forward to questions, and I'll hand it back over to Amara.
And now we will move on to the Q&A portion of the event. Gerald, Dwayne, we've had questions pouring in. So I guess we'll start at the very beginning. Gerald, I'm going to toss one to you. Kyle from Dallas asks, what code defines the bypass isolation switch? What is required for life safety loads?
Okay, that's an excellent question. It's not that explicit. The code talks about, and when I'm saying the code, I guess I should reference it specifically, NFPA 110 and 99 both talk about bypass isolation switches and where they're permitted, but the requirement for having a bypass isolation switch really is triggered by the 110 requirement to maintain your transfer switches. So by their nature, life safety and critical loads can't be taken offline. So the only way to maintain those transfer switches is to add that bypass isolation feature. Wouldn't be required on the other loads because you would be able to take them online to maintain them. That's clean contacts, all the scheduled maintenance that needs to happen to those type devices.
Yeah, actually, to add to that, Gerald, in the state of California, with OSHPD, they actually require that your hospital transfer switches have to be bypass isolation type. So it's prescriptive for their jurisdiction.
Yeah, it definitely. We can add that asterisk to almost all these answers. Is that varies jurisdiction to jurisdiction, but.
All right, excellent. Thank you both. This next question, Dwayne, I'm going to throw out to you. Cliff from Austin is shifting gears here. He wants to know a little bit about combined heating and power. He asks that you clarify opportunities to redirect funding that is planned for prescriptive or life safety or critical power and comply with that requirement, natural gas CHP system that runs 24/7. I guess what he's asking is about NEC 702, which standby emergency generators can be deleted. Can you highlight that a little bit?
Okay, well, that's about an hour-long discussion. Real quick, I think in the systems that we design, especially when you're dealing with a larger scale distributed or aggregate paralleling system, there definitely are opportunities to do combined heat and power. In Las Vegas, it doesn't make a whole lot of sense based on the cost of power and the cost of natural gas and our climate. But I know, places, we have partners that we work with in Atlantic City and also up in Connecticut where the combined heat and power makes sense. And now you can really leverage the generators not only for backup, but also for, other means to, combined heat power for the building or for cooling, drive an absorption chiller with it, cogeneration. There's so many different ways to go with that. So I think it would be easier for a large-scale resort to be able to get that on because they've already got this infrastructure in place to basically island the property, and the more efficient they can make that system, the better. Hopefully that answers the question, but that was a mouthful, Emma.
Yeah, well, it sounds like we've got a whole other presentation to work on here, Dwayne. All right, I'm going to send you this next question as well, Dwayne. This is an interesting one from Cliff in Austin. Many operators of electric grids offer incentives to make on-site generators participate in meeting peak electrical demand based on the input signal from the power grid operator. So I guess he's talking about demand response here.
Yeah.
Can healthcare or a casino participate in the electric grid demand response programs? What are the applicable codes here?
That gets interesting because now you're talking about you're going to be generating into the, well, it depends on how it's structured. We've done it for hospitals in Southern California. Everybody probably remembers when the rolling blackouts were occurring. One of our clients would actually get an alarm from the utility, and they would transfer a lot of their load to their on-site generation. So there's a couple of things to talk about. If you're talking about taking your load shedding the grid and taking your load off the grid to free up capacity, we've seen that as an option. When you start talking about generating into the grid, which actually here in Las Vegas, North Las Vegas, Apex is a site where we're actually doing that with a large turbine. That's typically a different type of system and different type of system than you would have for backup to a property. But as far as demand management and helping the utility out, we've seen that all over the country where, particularly on more remote properties, the utility will call on them in August or, at their peak time and ask them, hey, can you take some of your load to generator? And they're incentivized to do that. As far as what codes apply, other than 705, it really is going to come down to whatever the interconnect agreement is with the utility.
And I'd like to jump in on that a little bit. We've had a lot of requests from our utilities, from our clients. These agreements, I guess, can be quite lucrative to our end users, certainly down in southeast portion of the United States. The big thing that changed recently is the Tier 4 requirements or our EPA requirements. And so once you enter into one of these agreements, you've got to tread very carefully on your runtime and whether your standby generator just became a prime generator, and now you have to honor and follow all these regulations that are outlined by the EPA. It can be quite expensive.
Yeah, that's a really good point, Gerald, because the emissions become a really big deal, and even your air quality management districts for the local area would be another discussion that would want to be you'd want to engage, because that is a huge issue in terms of cleanup of the emissions.
All right, very good. Gerald, this next question is going to come to you. We've had a couple questions about this. Michael, William, a few different people have asked you to explain wet stacking. If you could go into a little bit more detail.
Oh boy, wet stacking. It's probably a slang term. It's the term that we use for the undesirable effect on the generator exhaust system for running a generator lightly loaded. And all of the testing and NFPA 110 and even 99 to some degree is built around trying to avoid that condition, because the last thing you want to do when you test this generator every month is be hurting it and causing it to have, generating a failure mode for that unit. And so, and the code has changed a little bit depending on which 99 and 110 have been adopted in the various jurisdictions on that percentage of load. It's 30% for the monthly test. The annual test had a 25% benchmark. I think most generator manufacturers want 50%, to make sure that they don't have this condition occurring in their generators.
And that's one of the big challenges, Gerald, with when they just turn the engines on. If they're not running the engines under load, then you get that tarry buildup on your exhaust output, and it just, it's going to actually, eventually it'll foul your system.
Yeah.
All right, excellent. I have a question that perhaps both of you can chime in on, because he's asking about different jurisdictions across the United States. George asked, do you find many jurisdictions that enforce the strict interpretation of selective coordination? Gerald, do you want to start on that one?
Oh, sure. I'd enforce strict interpretation? No. I would say the majority of jurisdictions I work in have not traditionally enforced that. It's part of our culture at the firm I work at that we always generate a selective overcurrent protection study for everything we're doing. I know that the language has consistently been strengthened within the NEC, and certainly people are waking up about it, but enforcement, no, I don't see a lot of it. What about you, Dwayne?
Well, we see it in the design side, but like you guys, Gerald, I mean, we use analysis software, SKM, and there's others out there, but we run on our 15 kV system down through our 480 volt systems, just making sure you're selectively coordinated. It's really just prudent design when you think about it. I mean, isolate the device that trips to only that's closest to the fault makes a lot of sense. I mean,
it makes a lot of sense, and please realize that my experience is in hospitals. It's just not even a risk that we can consider to have a device nuisance trip because it is poorly coordinated, and it's a loss of life issue. That's something we just can't tolerate.
Good, thank you. This next question for you, Dwayne, is about code. Wayne asks, does NFPA 110 apply to prime-rated diesel generators used as the primary power source system for multiple facilities?
Well, I think that probably, if you've got a primary source generator, then it wouldn't fall in the emergency and standby power systems category. So it would put you in a different, as a primary source of power, you've got a different set of codes that you would go with. Off the top of my head, I don't know what they are, but just by 110, the title of 110 is Standard for Emergency and Standby Power Systems. If you're using a unit as a prime power unit, clearly it's not really for standby, and I guess you would have to shut it off so that you could test it. I mean, being facetious, if it's a prime source, then it's gonna fall under a different category.
Very good, thank you. This next question, this is more of a question, I guess. Thomas is trying to take our exam, which you can take by going up to the links option at the top of the screen. And he says, the exam uses emergency in a couple of questions when the intent seems to imply emergency applies to all loads on a generator. Is this true?
That's actually really interesting because, I mean, emergency, and Gerald, you can jump in here anywhere, but emergency is, for me, is it's 700 in the context of the presentation and anywhere that I would use it. Gets a little squirrely in the medical side, and maybe I'll let Gerald take that one. The reference to essential power system and emergency system.
Yeah, that's probably, if there's any blame, it's probably one of my questions. It's an old catchphrase that really is way too general to be used, and is not specific to essential or standby or all the language that Dwayne did such a good job of presenting. So apologize for that if that's causing some confusion.
So, but Gerald, in a hospital though, is life safety and critical are considered the emergency, right?
They're considered the essential.
Essential?
What we refer to, yeah, the essential.
And equipment branch falls in there with it, correct?
That is part of the global emergency system, I guess.
Okay.
All right, thank you for that clarification. We have time left for one more question, and I'm going to throw this out to both of you. This is an interesting question from John in Houston. He says, I do peer reviews on community safe rooms or storm shelters, typically the size of a gym. ICC 500 requires both emergency and standby lighting and standby power. Is there any guidance that you can give him?
Yeah, size of a gymnasium. Yeah, he's probably, he's got 3 transfer switches and he could do everything with one is probably what he's thinking. You want to take that one, Gerald?
No, I don't do many gymnasiums, but or emergency, emergency shelters there. I know the language and the code keeps changing, the NEC, and basically they're trying to make all of these required to be separate systems. So I think the days of combining up essential, non-essential, and these various life safety branches into one big transfer switch are gone. And my recommendation is I would like to see separate transfer switches for those loads, but I'm also be the first to admit that I've not ever designed that type of facility.
I'd like to say thank you. That's a terrific explanation in the short amount of time we have. I would like to close by thanking our terrific speakers, Gerald Versluys and Dwayne Miller, for generously sharing their time and expertise. Finally, on behalf of CFE Media and Consulting Specifying Engineer, I'd like to thank you, the audience, for attending. This now concludes our webcast. Goodbye.